Have you ever been graphing an equation and had just part of it disappear, or when you're going through an algebraic problem and it comes into a non-existent number, possibly 0 over 0? Well, those things are called limits, and that's what me, Lachlan, and my partner Jovan will be explaining to you today. So we'll start by graphically explaining what limits are. And so in this equation, y equals x squared minus 7x plus 10 divided by x minus 2. You can see that at the coordinate point 2 comma negative 3, there is an empty circle there. That's called a removable discontinuity, and that means that there, in the parameters of the equation, there is no value at that point. And so graphically, that shows that the limit as x is approaching 2 of this equation is going to be negative 3 just by eyeballing it, but you can't mathematically prove that in this just by looking at the graph. There is one other scenario, though, with graphs where you can't actually tell what a limit is by just looking at the graph. Because in this instance, in our function f of x, So as we can see at the coordinate points 5, comma 0 and negative 5, comma 0, there are both removable discontinuities. So if you were asked the question just by looking at the graph to find the limit of this, you'd actually, the answer would be DNE or does not exist, because if there's, I guess technically 2 limits for the same value, but you can get asked the question that would look like this of find the limit as, let's see, limit as x equals 0 from the right. So it would be this equation here. That's what it would be asking. You can give an answer for that limit because it's only asking for one part of the equation or for one value as it approaches from the right. Then you can do the same as it approaches from the left. And so this plus sign means it's approaching from the right, and this minus means it's approaching from the left. So from the right, you can easily say that the value is 5 for the limit, and then as it's approaching from the left, negative 5. But again, the answer to this would be DNE, as it's asking for both sides, which you can't have 2 limits for the same value. So for proving a limit numerically, we've taken the equation that you saw in the first graphic representation of limits and plugged it into our calculator, and then took the shown tables and wrote them down. So for this first part here, you can see that as x equals 2, the calculator gives an error, meaning that it can't give you a number for that x value. So what we did to numerically show where that limit is, in the table, we made it, so we put x values getting infinitely closer to 2, and we'd get y values infinitely closer to negative 3. And so we did this for both just below 2 and for just above 2. And in both cases, it showed that as x gets infinitely closer to 2, y gets infinitely closer to negative.
The final way that we can find the limit is algebraically, and here we have the equation limit of as x approaches 2 of x squared minus 7x plus 10 over x minus 2. So what we want to do is plug in the 2 into the equation, but if we do that here, we get a 0 on the denominator, and that makes it an invalid equation. But what we can do is simplify it. So to simplify it, we're going to simplify x squared minus 7x plus 10, and we can factor out an x minus 2, and we can get x minus 2 times x minus 5 over x minus 2. And we can cross out the x minus 2's, and what we're left with is x minus 5. And we can plug in the 2 into this equation, and what we get is 2 minus 5, and this equals negative 3. So the limit as x approaches 2 is equal to negative 3. The definition of a limit is the value that a function or sequence approaches as the input or index approaches some value. For our our reflection, why we chose this topic, we had just finished learning it in class. We didn't want to have forgotten it by the time of the final, and we wanted to refresh our memory. Also, limits are very common in calculus, and we see them a lot. So we learned how to graphically, numerically, and algebraically find limits. And we also learned that sometimes the value for a limit does not exist. For example, in our second graph that we showed you in our project.